Okay, hello everyone. Um, Welcome back to ergodic theory, etc. Let me just remind you, it's helpful for me if you share your video, if you're willing. I do finally have uh, a separate monitor to see the gallery view nicely. And here's a picture I'm going to come back to today. Who knows what this is a picture of?
Is it a picture of a toral automorphism?
Yes. I have trouble getting simultaneously speaker view and okay, was that Ethan?
Yep.
Okay, yeah, go ahead. Can you say a few words about that?
Oh, sure. Yeah. So when I say toral automorphism, I'm thinking of essentially the action of a matrix in SL2Z that you've projected onto R2 mod Z2 because it preserves the integer lattice. And these things, if they're hyperbolic, they have very nice mixing properties.
Right, so that's something we're going to develop today from the point of view of spectrum. The main thing to notice in this picture, this is really the first picture I've shown of really the evolution of a set under dynamics. So we start with a round ball on the torus. The torus is the square with opposite sides identified. And then the map is essentially linear, and it stretches the torus to an ellipse, and then that ellipse gets very long, so long that it looks like a sheet of rain in the last picture. And the set we started with ends up spreading or mixing all over the torus evenly. And so that's one of the themes we're going to develop today, and that's very different, of course, from what happens with the irrational rotation. Okay, so let me switch to the Blackboard. If I can do that. Any questions before we get started? Okay, so I want to start today with some general results and then go to a couple of specific examples, including the one we just saw. So perhaps one of the general results I should prove is the ergodic theorem. And there are various versions of this theorem, as you know already. So we have Xm is our probability space, and we have an automorphism T, and then the quantity we're interested in examining for some function x is the average of its values, 0 to n minus 1 of f of t I x. So the average of its values along an orbit. And there are a couple of different versions of the result, but what we've proved already is the von Neumann version, which is for f in L2 of x, so that we have inner products and we can talk about the projection to the invariant functions. And the theorem here was that, that Sn of f tends in L2 to P of f. And P of f is just the projection of f to the part of it that's invariant under the action of t. So this is the projection to the t invariant functions, which form a closed subspace of L2. And of course, when the map is ergodic, the only t invariant functions are the constants. And so this P of f is just equal to the constant function, which is the average value of f if t is ergodic. So notice that the ergodic theorem actually, although it has the word ergodic in the name, it applies even when the transformation t is not ergodic. So this theorem was pretty easy to prove. The next theorem is trickier, and it's usually phrased for f in L1 of x. It's slightly more delicate. That's a broader class of functions. And it says that Sn of xx, that this converges pointwise for almost every x to some function f bar of x, which is t invariant. And again, when in the ergodic case, the only t invariant functions are the constants, and since remember that the integral of Sn of f is equal to the integral of f for all n, because the measure is preserved. So this function at the end must just be the integral of f in the ergodic case. I heard a comment, but can you repeat? Was there a comment? Okay. Anyway, it converges to the average in the ergodic case. And this happens pointwise. Now you might say, isn't pointwise convergence in L2 just some silly technical issue? But it's not really, because remember that you can have functions in L2 that are converging to 0. So here's an example of a sequence of functions tending to 0 in L2. They're called the blimp functions. So you say you're on L2 of 0, 1, and your function is 1 on an interval and 0 on the adjacent interval. And then this interval, the blimp flies across, and it's 1 here and 0 there. And then the blimp gets shorter, and it slowly flies across the interval. Then it gets smaller and it flies across the interval again. And since the support of the function is tending to 0, it definitely converges to 0 in L2. But if you stand at one particular point, you see the blimp fly over infinitely often. So you see the sequence 0, 0, 0, 1, 0, 0, 0, 1, and it doesn't converge in pointwise. And so this is definitely a stronger theorem that we have pointwise convergence. And as I mentioned before, this implies, for example, the strong law of large numbers, that if you flip a coin, a fair coin over and over again, then almost surely the average number of heads you'll see is 1/2. Okay, so what we're going to do is I'm going to prove a version of this theorem, but in the case that's of most interest to us, which is not a function in L1, but the indicator function of some set of positive measure. And then this Sn is just counting the percentage of time that we spend in this set A. Okay, so we've taken our space X, we've distinguished a subset A, and now we're looking at an orbit, and we want to prove that the percentage of time spent in A, well, if the map were ergodic, we'd try to prove that that converges to the measure of A, but maybe it's not ergodic. Well, then all we really want to do is prove it converges. And then you might say, well, what good is that? What does it converge to? But we already know what it converges to. That's given by von Neumann's theorem. It converges to the projection of this indicator function to the invariant functions. And the only issue then is, does that convergence pointwise rather than just in L2? Okay, so that's the version of the ergodic theorem I want to explain. And the proof of this version, the L1 version, is fairly technical. You can find it in the notes. And it has an interesting history. I think von Neumann, when he proved this theorem, he considered this essentially obvious. It follows easily from the spectral theorem. The proof we gave was just slightly slicker. But this was a hard theorem to prove. It was proved by Birkhoff and Hintgen. And there was lately discovered by Kamei a very simple argument, much simpler than what's been produced in the past, and it's especially easy to explain for the indicator function of a set. So that's the proof I'm going to give today. Okay. And the interesting thing perhaps about this proof is somehow all of these proofs are essentially combinatorial. In some sense, even Poincare recurrence is combinatorial. This measure preserving map is some sort of advanced form of a permutation, And we're just looking at what properties of a permutation can have. And this theorem is saying that a permutation can't be very unbalanced. It can't sort of visit A a little bit some of the time, and then a lot more later, and then only a little bit some of the time. It has to spend a sort of even amount of time in A, as you would expect for a finite permutation. Okay, so let's address this theorem. Let me state it clearly. So we have our measure preserving map T, and I'm going to let F be the independent function of A, where A contained in X is a measurable set. And just for brevity, I'm going to write this also as Sn of X. And now, this function, which is measuring the amount of time you spend in A, obviously this indicator function is just 0 or 1. So this function is always between 0 and 1. And the issue is just, does it oscillate? And so it certainly has a finite limb sup, and it has a finite limb inf. And so we can look at how it oscillates between its limb sup and its limb inf. And what we're trying to rule out is the behavior that when we look at Sn as a function of n, that it goes up and down like this, that it oscillates. But whether or not it oscillates, we can still define the upper limit of x to be the limb sup as, S bar of x is the limb sup as n goes to infinity of Sn of x. And similarly, the limb inf. And what we will show is, so the theorem is going to be that Sn of x converges AE. And in fact, this is implied by the following simple lemma, simply stated lemma, which is that the integral of the limb sup of S over our space is greater than or equal to the measure of A. Less than or equal to the measure of A. Because this same argument, or replacing A with its complement, will show that the integral of the limb inf is greater than or equal to the measure of A. But this function is bigger than that function, and so if they have the same integral, they must agree almost everywhere, and therefore you have convergence because the limb sup agrees with the limb inf. Okay, so this is what we really are going to show, is that when you integrate the limb sup, you get something that's bounded by the measure of A. And see, you see the tension there. You might think A is a small set, but somehow every now and then we spend a lot of time there, and then the limb sup would end up being bigger than the measure. That doesn't happen. That's what the lemma says. Okay, and the proof is quite slick. So we pick an epsilon greater than 0, and we let tau of x be the least n such that Sn of x is greater than or equal to its limb sup minus epsilon. So remember, the sequence is oscillating up and down. It has to come close to its limb sup infinitely often. And so in particular, there must be some point where it's within epsilon of its, some time where it's within epsilon of its limb sup. And now, just to make life easier, let's suppose that tau x was less than or equal to some constant n for all x. So within capital N steps, you get within epsilon of your limb sup. And now let's choose, actually let me call this k. And now let's choose an n which is much, much bigger than k. And so we look at our average from 0 up to n, and we can group this average into various smaller times where, say, this first average is over tau of x steps. And then we stop there, and then here we go over tau. Actually, let me call these x0 up to xi. So then we go tau of xi steps, and then we go tau of xj steps, and so on. So in other words, we take this very long average and we break it up into pieces, and on each of these pieces, the average is very close to s bar of x minus epsilon. Well, if you have a lot of pieces like that and the average is within s bar of x minus epsilon, each of those pieces, then the average from 0 to n is also at least s bar of x minus epsilon with a small error. So then s bar of x, for that particular value of n, s capital N of x is greater than or equal to s bar of x minus 2 epsilon. Okay, once you've taken this to be large enough. But now, just integrate both sides. The integral of Sn of x is just equal to the measure of a. And this is greater than or equal to s bar of x, the integral of s bar of x, minus 2 epsilon, because the total mass of the space is 1. And so this being true for every epsilon, you can just erase the epsilon here, and you get that the measure of a is an upper bound for the integral of s bar. That's the end of the proof. Okay, so now the question becomes, yes, that was fine, but you assumed this uniform bound on the amount of time it takes to come within epsilon of the limb soup. How can you fix that? Well, the great thing is this: for any particular point, there is a finite k for which you come within epsilon of the limb soup. So there's a certain set where k is 10, a certain larger set where you can take k tau of x is less than 100, a larger set where it's less than 1,000,000, and then the union of all of those exhausts the whole space. So if you're willing to throw away a small part of the space, you can achieve this fact. So actually, we have that tau of x is less than some specific k for all x not inside some exceptional set E. So this we have for sure, and by taking k large enough, we can choose that the measure of E is itself less than epsilon. Okay, so what we wanted to make the first argument work does work, except when x happens to fall in this exceptional set E. And now we do something really brilliant. This is the most brilliant step in the proof, is we take our original set A and we add to it this exceptional set E. Just throw these bad points into A, and you get a new set A prime that's just slightly bigger. And now we rerun the argument for A prime, which has A union epsilon in it. And so what happens there, there's these places where tau of x is small, and they're good, and then there's the places where tau of x is big. Well, that's where you're in the exceptional set, but the exceptional set has been thrown in there. So here, when you're looking at these SNs, you're getting 1 at all of these points. You're in the set. And so the old argument works when tau of x is small, and the exceptional set being in here makes the sum just bigger because you've thrown it in. So what we get is the same inequality, but now it's Sn prime of x rather than Sn of x. In other words, it's what we get for the indicator function of A prime instead of A. Okay, but once we've gotten to this step in the argument, we then get that the integral of Sn prime of x is bigger than the integral of S bar, minus 2 epsilon, which is good. But the integral of S prime is now the measure of A prime. So this is equal to the measure of A prime. And that is less than or equal to the measure of A plus the measure of this exceptional set, which is epsilon. And so the whole thing is correct to within 3 epsilon, which gives the result that we want. Okay, so that's this rather clever modern proof of the pointwise ergodic theorem. And I should mention that there's many arguments in dynamics where one uses the pointwise ergodic theorem, but with a little bit of extra thought, you could have used the L2 version due to von Neumann, which I guess I've erased now. Sorry, I don't know what I'm pointing at. So either one is adequate for most arguments. But the pointwise one is very important from a philosophical point of view, because at the end of the day, if you're trying to do celestial mechanics or physics or if you're trying to do even statistical mechanics, the description of the gas in this room, and you make some ergodicity assumption, our universe is one point in phase space. It's not some average. And so what we want to know is what happens at a randomly chosen point in phase space over all time. And that's a pointwise issue, not as some sort of convergence in measure. And for that reason, the ergodic theorem is really important. Similarly, when you have a sequence of random events, there's a big difference between saying that that you have the strong law of large numbers, which says that the coin flips converge to a half, versus the weak law, which would say that in some average sense they converge to a half. Okay, so that's the deepest theorem in ergodic theory that we've discussed so far. So what I want to do now is return to the discussion of spectral invariance and discuss the general theory, but also present two examples, which we really will want to keep in mind as we look at more sophisticated dynamical systems like geodesic flow. They're going to be the two extreme examples of measure-preserving dynamical systems. So let me go back and briefly recall the spectral theory. Of a unitary operator. So the idea was that every unitary operator can be described by a measure on a circle plus a multiplicity function. So if given mu, which is some measure on S1, and M, which is some measurable map from S1 into 0, 1, up to and including infinity, we can build this space L2 of mu m. And on this space consists of certain functions on S1. I'm going to give you a description of this space that's slightly different than what I gave last time, just for the sake of variety. So the Hilbert space associated to these two notions will be maps from the circle into little L2 of the natural numbers. Let me remind you what this is. This is just the set of sequences, A0, A1, etc., such that the sum of the absolute value of the AI squared, which is the norm of A squared, is finite. And so we have, at every point, we are given a sequence, Fi of lambda. And there's an obvious L2 norm on this space, which is that the norm of F in L2 squared is the integral over the circle of the norm of F at lambda, which is a point in little L2 squared with respect to this measure mu. Okay, now where does the multiplicity come in? The idea is that when m is equal to 1, you're not allowed to use all of little L2. You're only allowed to use a one-dimensional subspace thereof. When m is equal to 2, you're allowed to use a two-dimensional space. This is to take into account sort of multiple eigenvalues and the like. So to say that rigorously, what we say is that Fi of lambda is equal to 0 if I is greater than or equal to m of lambda. So over the locus, where m is equal to 1, only F0 is allowed to be non-zero. So remember, this is F0 of lambda, F1 of lambda, etc. So over the locus where m is 1, the values, F takes values in a one-dimensional space. Where m is 2, it takes values in a two-dimensional space. But where m is infinite, it's allowed to use the whole space, little L2 of m. Okay, now here's a general fact. On L2 of anything, you have an action of L infinity of mu m. Namely, if you pick a function g that's uniformly bounded, it determines an operator, which is Sg of f is just g times f. And the operator norm is just the sup norm of g. It's definitely bounded on L2. And what's the adjoint? The adjoint is just g bar, the complex conjugate of g. So S star g bar of g is S of g bar. And of course, multiplication by g and g bar commute. So this action, all of these operators are normal. And when are they unitary? They're unitary when the absolute value of g is 1, because then it doesn't change the L2 norm, right? Because the L2 norm involves the absolute values here. So the typical example of a unitary operator is just multiplication by a function of modulus 1. And in particular on this space, we can multiply by the most obvious function of modulus 1 other than a constant. Namely, we define L of f to be the new function lambda f of lambda. And of course, lambda is ranging in the unit circle. And so this function has modulus 1 everywhere. This is a unitary operator. And the idea is that on the part of the circle where when we're close to some value lambda naught, the functions supported near that point are approximate eigenfunctions with eigenvalue lambda naught for this operator L. And then the spectral theorem says that for any unitary operator U, and technically we should say on the separable Hilbert space, it's modeled on one of these. So there exists an isomorphism, we call this space H, an isomorphism to some L2 of mu_m that sends the action of U to the action of multiplication by lambda. Okay, so that's the general statement. And as I mentioned last time, the pair mu_m is almost uniquely determined by the unitary operator U. It's actually, if you take a different measure, but that has the same sets of measures 0 as mu does, it actually gives an isomorphic operator. So, so we now have a procedure for studying measure-preserving transformations. This is called the spectral point of view. So we go from T, morphism of X, up to U, which is a map on L2 of X, and given, of course, by U of F is F composed with T. This is unitary because X is measure preserving. And then we go from this to the spectral invariants of U, which are a measure on the circle and a multiplicity function. And so this is a way of analyzing an arbitrary transformation T. And as I mentioned before, the whole point of this is that unitary operators are never act irreducibly on Hilbert space. They always have invariant subspaces. So you always have some sort of non-trivial decomposition into eigenspaces, except that you have to allow for a continuous decomposition, which is what this measure permits. So even if T is irreducible, being ergodic, U is not, and that's what's recorded by this information mu_m. Okay, so let's look at two examples of what this measure is. So let me just start over again here. Two very basic examples of how this spectral theory works. So first is if U is a map on a finite dimensional Hilbert space, then the spectrum of U is some finite set of numbers, lambda 1 up to lambda n, all distinct. And the spectral measure can be taken to be just the sum of delta functions of these lambda i's. So you should picture the circle And then there's a little star. This is called point spectrum at each of the eigenvalues. That's what the measure looks like. And then what's the multiplicity function? The multiplicity function tells you how big the eigenspace is. So m of lambda is the dimension of the kernel of u minus lambda, lambda minus u. And so that's equal to 0 unless you're at one of these eigenvalues. And at the eigenvalue, it tells you the size of the eigenspace. So this is a function that takes finitely many values. And then u itself is just, what does it look like? Well, you see the first eigenvalue repeated m of lambda 1 times. And then similarly for the second eigenvalue all the way down to the nth. Okay, so that's, u can always be diagonalized, and this is just a fancy way of recording the list of eigenvalues and their multiplicities. Okay. So that shows that the spectral theory captures the usual theory of diagonalization. But it's the most interesting when you have an operator that has no eigenvectors. And here's the most fundamental example of an operator with no eigenvectors. So we take the space L2 of Z, which is the space of sequences indexed by the integers, and we look at, sorry? And we look at the operator that takes a sequence and shifts it along. So it's AI minus 1. Okay, now why doesn't this operator have any eigenvectors? Who can explain?
Because you always need like the first n coordinates to be 0 for like any n.
Well, what if the first coordinate was not 0?
It needs to be square summable, so they can't all be the same unless they're all 0. They like change somewhere, but
yeah, that's right. So if you had UAI was equal to lambda AI minus 1, then up to a constant, you would get that AI, the sequence AI, is just the powers of lambda. And of course, that can't possibly be an L2, even if lambda is less than 1. Since it's unitary, that it would have to be on the circle anyway. So this operator has no eigenvectors simply because, as was mentioned, the elements of this space are sequences that go to 0 at infinity. So you can't have something that, when you shift it over, it gives you a constant multiple of itself. So this has no eigenvectors. So I think the first mystery in the theory of unitary operators is, how do you diagonalize this operator? Is this operator somehow nilpotent? Well, it's not, because it's unitary. The size of a vector remains the same as you iterate. It doesn't tend to 0. So how should you think of this operator? And the theorem is that U has Lebesgue spectrum of multiplicity 1. In other words, we can take the mu to be just length measure or Lebesgue measure on the circle. Remember, it doesn't matter how we normalize this by a constant. Those all get the same measure class and hence the same spectral information. And the multiplicity function should be identically equal to 1. Okay, so let's not worry too much about the statement. Just look at the proof. So the proof is based on the fact that these sequences AI are nothing but the Fourier series of L2 functions on the circle. There's an isomorphism between little l2 of z and little l2 of s1, which just sends the sequence AI to the function f of lambda is the sum of AI lambda to the I. And now what does the shift operator go over to? Well, if you multiply lambda, f of lambda times lambda, what you get is the sum of AI lambda to the I plus 1. which is the same as the sum of ai minus 1 lambda to the I. So all you've done is you've shifted the coefficients over by 1. So in other words, the action of u here goes over to the action of multiplication by lambda here, which is exactly what we want for the spectral theorem. So in other words, this L2 of S1 with respect to d lambda, this space is the spectral model for this unitary operator. So you can see we now have a different picture to try to visualize this punctual spectrum in the finite dimensional case has become smeared out to a measure on the whole circle. And there are no eigenfunctions. But if we take a function in L2 of the circle that's supported in a small interval around some number lambda naught, then the action of u will almost be multiplication by lambda naught. It will just never be that on the nose. And that's the idea of what a general unitary operator looks like and how Lebesgue's spectrum stands in for the simpler decomposition into eigenspaces that's familiar from the finite dimensional case. Okay, so this is a type of unitary operator that occurs over and over again, and it's simply described by saying it has Lebesgue spectrum. It corresponds to the shift map. It corresponds to multiplication by lambda on L2 of S1. Okay, so now we are ready to look at our two favorite examples. So our first example of a measure-preserving transformation is the rotation of the circle, an irrational rotation. Say, let me write this as t of z is alpha z. Z will be in, I'll think of this as the unit circle in the complex plane, and then alpha will also be a complex number of absolute value 1. And of course, the statement that it's irrational is that alpha is not a root of unity. Okay, so what's the spectral decomposition of this operator? Well, we're very lucky. We just wrote down a nice way of thinking about L2 of S1. Namely, it has this Fourier decomposition. The functions z to the I in S1 are an orthonormal basis for L2 of S1. So L2 of S1 has a basis, an orthonormal basis. We normalize so this is a probability measure, given where ek of z is just z to the k. And beautifully, this standard orthonormal basis is actually a basis of eigenfunctions for t. So t is simply diagonal with respect to the obvious basis for L2 of S1. In fact, if we take ek composed with t, which is what we would call u of ek, then we just get alpha z to the k, which is alpha to the k times ek. So the eigenvalue of the kth element in the basis is just alpha to the k. And our conclusion is that mu, the spectrum, is just a sum of delta masses at the various powers of alpha. So mu is equal to the sum over k of a delta mass at alpha to the k. Now, you might say, oh, I want to have finite measures. I don't like having this countable sum of delta masses. That's fine. Remember, all that matters is what the sets of measure 0 are. So if you prefer, you can divide these by 2 to the k. You'll get the same measure class and an equivalent spectral model for the map. And then, of course, each of these eigenvalues is simple. These values alpha to the k are distinct because alpha is not a root of unity. And so the multiplicity function can just be taken to be equal to 1. And you could set it equal to 0 on the rest of the circle, but it actually doesn't matter what its values are outside the support of mu. Okay, so this has, how do we describe this operator? The standard words that are used here are that t has pure point spectrum. That means L2 decomposes into an orthogonal direct sum of eigenspaces for T, finitely many or countably many. Okay, so T has pure point spectrum. Okay, so almost a little bit too easy, but still illustrative of how you could use the spectral theorem. So here's a corollary that you could prove in an elementary way, but it's now obvious because of the fact that the spectrum is an invariant. The corollary is that if you have two irrational rotations, they can't be measure preserving conjugate except in the obvious case. And what's the obvious case? It's where if you have irrational rotations by alpha 1 and alpha 2, then if alpha 1 is alpha 2 to the plus or minus 1, then they're obviously measure preserving conjugate. And the claim is that that's the only time that they're measure conjugate because you can recover the subgroup generated by alpha from the spectrum of T. Namely, it's the support of the spectral measure. And that subgroup has a unique generator up to plus or minus 1. So let me just write that. As a corollary is that T alpha 1 is isomorphic to T alpha 2 as a measure preserving system. If and only if alpha 1 is plus or minus alpha 2 to the plus or minus 1. Okay, so our next example is more interesting, and it's representative of a lot of phenomena that arise all throughout dynamics and ergodic theory. And it will be the picture that I showed you at the beginning of today's meeting, namely a linear map on the torus. So let me describe what these are, then say what their spectrum is, and then say how we prove that. Okay, so our space is going to be R2 modulo Z2. And our transformation is going to be given by an element of GL2Z. That is a matrix with entries in the integers and determinant plus or minus 1. So its inverse is also an integral matrix. And how does this determine a map on the torus? Well, this gives a map from R2 to R2, surjective invertible map, a bijection because its determinant is plus or minus 1, and it sends the integers bijectively to the integers. So it descends to a map on the quotient space. So usually one expresses the map as a matrix, but then thinks of it as defining a transformation. And I won't introduce a separate notation for that. We'll just call everything T. Now, there are 3 different types of transformations on R2, coming from these matrices with integer coordinates, and actually even with real coordinates. We say T is hyperbolic if it has distinct real eigenvalues. And in this case, this is the case that we're going to be interested in studying, the action of T on R2 is very easy to understand. So on R2, there's some eigendirection which is expanded by one of the eigenvalues lambda 1. By the way, the eigenvalues lambda 1 and lambda 2 have the property that their product is the determinant of T. So lambda 1 is equal to lambda 2 inverse up to a sign. And in particular, one of the eigenvalues is bigger than 1, and the other one is less than 1. Let's see, should I worry about the case where one is 1 and one is minus 1? I guess I should. let's say where the absolute value of lambda 1 is bigger than 1, bigger than the absolute value of lambda 2. Okay, so there's an expanding eigenvalue and there's a contracting eigenvalue. Usually their eigenspaces are not orthogonal. And if we look upstairs at how this dynamics acts on a small ball around the origin, it's pretty obvious. In the lambda 2 direction, this ball is compressed, and in the lambda 1 direction, it's radically expanded. Now, the magical thing about this operator is that even though it's sending most points in R2 to infinity under iteration, it has the property that nevertheless, it sends the integral lattice into itself. That's because of the fact that we chose it to have integer coordinates. And in particular, since the determinant's plus or minus 1, it's also measure preserving. Now, what are some other possibilities for an element of TO2Z other than hyperbolic? Maybe every element is hyperbolic. Are there any elements that aren't hyperbolic?
You could have a single Jordan block.
A single Jordan block, right? So you could have a map like T is 1, 1, 0, 1. Or in other words, you could have a single eigenvalue of multiplicity 2 rather than 2 distinct eigenvalues. And when you have multiple eigenvalues, then and T is of infinite order, then T is said to be parabolic. So what's happening here is the map preserves one of the coordinates and it's a shear in the other two coordinates. So this is T of xy is, let's see here, this is x plus y comma y. So this parabolic transformation preserves the value of y. So it leaves invariant the horizontal lines in the plane. And that means that when it descends to an automorphism of the torus, well, each of these horizontal lines is invariant under a cyclic subgroup of Z2. So it means it preserves a foliation of the torus by lines like this. Each leaf here is sent to itself, and the map just twists the torus while keeping these leaves invariant. So this map is manifestly not ergodic. Because if we took any little bundle of leaves here, took a little interval transverse to the foliation, and then took all the leaves it meets, that would give an invariant set A of positive measure. Indeed, there is a map of this to the circle, which is invariant under the action of this twist T, and any function on the circle pulls back to a T invariant function on the torus. So there's too many T invariant functions. So that's another possibility. And then the only remaining possibility is that T has finite order. And of course, when T has finite order, there's no chance for it to be an ergodic dynamical system. So that's called elliptic. That means T n is the identity for some n greater than 0. And in the elliptic case, ergodicity fails even worse. Okay, so if this is not ergodic and neither is this, you can guess that the hyperbolic transformations are going to turn out to be ergodic. And they're even going to be mixing, which is a notion we haven't quite formulated yet, but which will follow easily from what we're about to say about them. Okay, so now let me state the theorem. The theorem is that T is ergodic when hyperbolic. And it has Lebesgue spectrum of infinite multiplicity. this is very different looking from the rotation of the torus, which had this pure point spectrum. Now the spectrum is all smeared out. And what's the difference? T is still related, it understands and respects the group structure on the torus, but it's not a translation in the group, it's an automorphism of the group. And the automorphisms are much richer than the translations. And that's what's reflected in this more exotic spectral decomposition. Okay, now how should we analyze a transformation on the torus, the two torus? Well, we analyze it the same way we analyze the transformation on the one torus, the circle. Namely, we choose an obvious basis for L2, and we look at how it acts on that basis. So what can we say about L2 of the two torus? Well, just like L2 of the one torus, this space is isomorphic to little L2, now no longer of Z, but of Z2. And in general, big L2 of the D torus is isomorphic to little L2 of Z to the D. In other words, it corresponds to sequences Aij with the sum of the absolute value of Aij squared less than infinity. They're indexed by two numbers which naturally range in Z2. And indeed, there's a basis here. Again, it's just a Fourier basis for the torus, which can be written in many different ways. Let me think of this now as literally points in R2 modulo Z2. So I have to tell you on a point in R2 what one of these Fourier basis elements is. And it's simply B to the 2 pi I times the inner product between xy and ij. So ix plus j. And the point being that if you change x or y by an element of z2, by an integer, this quantity will change by an integer, and so the exponential won't change. The exponential descends to a function on the torus. It's basically like z to the I, w to the j on a product of two circles in the complex plane. So this is, again, an orthonormal basis for L2. Okay, so you might say, oh, we're almost done. Let's just check that these are eigenvectors. But they're not. But the way that they're not is easy to understand. So as I said, this should really be thought of as the inner product between xy and ij. So if you apply t to xy and take the inner product, it's the same as applying the adjoint of t to, or the transpose of t to ij and taking the inner product. And so the action of t on these basis elements is the same as the adjoint action of t on Z2. Okay, so t upper star Eij, which means if we pull back, that actually let me call this U, the associated unitary operator has the property that U applied to one of these basis elements, which I'll index by an element of Z2, is equal to the same basis element evaluated at the transpose of T applied to V. Okay, so it's looking unlikely that these will have many eigenfunctions, because remember, T transpose has the same behavior as T. It has the same eigenvalues, so it's doing this stretching and pulling and so on. In particular, it doesn't have any fixed points in the integer lattice. In fact, it doesn't even have any periodic points in the integer lattice. So if we look at the action of T star, which again has these two expanding and contracting eigendirections, if we look at its action on the integer lattice, first, since these eigenvalues are different from, since these eigenvalues are not equal to plus or minus 1, there are no integral points in the eigendirections. The eigendirections have to have irrational slope. And so, of course, the origin is fixed, but what do the other integral points do? They do what any other point does, namely, the contraction moves them closer to the origin, and then they're propelled farther and farther away from the origin, parallel to the expanding eigendirection. So what we see is that these basis elements give us a decomposition of little L2 of Z2 into a bunch of invariant subspaces. And the invariant subspaces correspond to the orbits of T star acting on Z2, which is not hard to understand. We now have a transformation acting on a discrete space. And what do its orbits look like? Well, it has one point that's fixed, which corresponds to the constant functions. And then all the other basis elements fall into countably many infinite orbits. And on each of these infinite orbits, the map T just translates one basis element to the next. So let me write that down. So the action of T on L2 of the torus is isomorphic to the action of T restricted to this direct sum over the orbits of T star of what we call little L2 of the orbit of T star. In other words, the span of this is orbit of T star on Z2. On Z2. And how does T behave on a typical one of these orbits? Well, it just moves the elements along from one to the next. So the action of T on the infinite orbits is just a shift map. In other words, it's conjugate to the action of the shift on little L2 of Z. So this is isomorphic to the constant functions coming from the unique fixed point at the origin. So these are the constant functions, plus the plus countably many copies of little L2 of Z. And on each of these, T acts by the shift. It moves one basis element to the next. And we already saw what this strange looking unitary operator is like. It doesn't have any eigenvectors, but it has Lebesgue spectrum. And since there's countably many different orbits of T star, there's countably many different copies of this little L2. And so in the spectrum, we see countably many copies of Lebesgue measure. And so this implies that the spectral measure of, and as usual, we throw away the constant functions because we already know they'll give a delta mass at 1 for the spectral measure. So it's often useful to define U to be the restriction of T to the mean zero functions, the orthogonal complement to the constants. The spectral measure of this operator is Lebesgue measure. Absolute value d lambda on S1. And the multiplicity function is equal to infinity everywhere. Okay, so that's the next step in understanding the spectral decomposition of unitary operators is to absorb this idea of how a hyperbolic toral automorphism behaves. Okay, so as a corollary of this, we have that T is ergodic, as I mentioned. Why is it ergodic? Well, remember, to be ergodic is the same thing as having a non-trivial invariant function. But if you had an F invariant set of positive measure, then its indicator function would give an eigenfunction for T, and you could then normalize it to have mean zero by subtracting off a constant. And so then you would get an eigenvector for T on L2 naught of X. So if there are no atoms in this spectral decomposition, if it's purely continuous, it has no eigenvectors, then the transformation T must be ergodic. So let me pause there and just take this occasion to observe that we now have several equivalent ways of thinking about ergodicity. And we see that ergodicity is really a property of the spectrum of T. So if all you can remember is the unitary operator associated to T, you can still tell whether or not it's ergodic. So let me make that clear by formulating the following statement. So the theorem is, so we let U equal T restricted to L naught of X, then the following statements are equivalent. So the first statement is that T is ergodic. I'll start with some spatial statements. If the measure of A is positive, then the union from minus infinity to infinity of Ti of A is the whole of X. That's equivalent, of course, to saying there's no non-trivial invariant set of positive measure. If there were, its union wouldn't spread out and cover all of X. So I should say A B up to a set of measure 0. The third version is that any T invariant function on X is constant A B. And then the fourth statement is that since we threw away the constant functions, we can say the only U invariant vector is 0. Because the elements of L2 naught are non-trivial functions. So if we had one that was fixed, it would be a T invariant function on X, other than the constants. And then finally, we can just say that the spectral measure of U gives 0 mass to lambda equals 1. In other words, mu of the singleton 1 is equal to 0. So the only danger with ergodicity would be detected by having for your spectral measure a delta mass concentrated at 1, because that would give you a mean 0 function that's invariant under the action of T. Okay, so that shows that this unitary operator, and indeed just its spectrum, detects whether or not we have ergodicity. And of course here we have no atoms, and so that proves that we have ergodicity for this toral automorphism. Okay, so I'm going to pose a question for a breakout room, and before I do, let me ask a question of the audience at large. How are the eigenvectors for U, eigenvalues of U, related to the eigenvalues of U to the n? If I know the eigenvalues of U, what are the eigenvalues of U to the n? So note, I'm not even asking a question about spectrum. This is a very simple linear algebra question.
Someone put in the chat, but nth power of the eigenvalues?
Yeah, the nth powers of the eigenvalues, thank you. So if you have an eigenvector and with eigenvalue lambda, then when you iterate U on it n times, it's still an eigenvector, it's just its eigenvalues change to lambda to the n. Okay, so that's a hint to the question I'm going to pose to the breakout room now. And the question is, well, the problem is give an example of some measure preserving T where T is ergodic, but T squared is not. In other words, show that ergodicity is not a very robust property. It's not invariant under replacing your transformation with one of its iterates. And secondly, when is T to the n not ergodic for some n? can you explain this in terms of the spectral measure for you? How can we detect when this strange phenomena occurs? Okay, so let me go to breakout rooms now for about 8 or 10 minutes. And so please introduce yourself to the other people, pick a reporter, and then try to come up with an example of A. And if you do, maybe you can also come up with a characterization of when that occurs in terms of the spectrum. And the hint that I've just given should be useful. Okay, so let me see if I can get this. Okay. Okay. See you in 8 to 10 minutes. Okay, so look, here's the leftovers. How's everybody doing?
Not bad.
Thank you very much. Yeah.
Wow. So Rohil, what are things like at Princeton? Are all of your classes?
Yeah, everything is online. I'm actually not in Princeton. I'm in Lexington, Massachusetts, my parents' house. Yeah. So much closer to Harvard. Yeah.
Okay.
Yeah.
Well, maybe someday we'll be able to have class in person. You can just come down.
Yeah, that would be very nice. Always gonna leap at the opportunity for some
Right.
in-person interaction.
Yeah. Sardar, where are you? You're muted. You're muted, Sardar.
Apologize. I am living in Cambridge. I am here. I didn't leave.
And it looks like you're in your office. Is that right?
No, actually, I took from Amazon some material and pasted to the wall.
Wow.
So
That's amazing. Are you teaching?
I am postdoc and I am working in computational neuroscience, but I am very interested in various computational techniques.
Yeah.
And yeah.
But do you have any teaching duties this semester?
No, but before in the summer I was teaching for a student in deep learning in NLP.
I see. Wow. And did you use this whiteboard for your teaching?
No, I just like sometimes to derive in the board. I actually prefer the chalk in the classrooms.
I see.
This is like just a simulation.
Right, right. Yeah, I used to have a whiteboard at Berkeley. It's not the same as
Yeah.
writing in Blackboard. So Carl, did you receive homework from the class today?
Yeah, I received, I think, 10, including a couple from students that are not taking this for a grade.
Wow, that's great.
Yeah.
So do you guys know a solution to the puzzle? We're sort of our own breakout room here.
Can you repeat? I didn't understand.
Do you know a solution to the problem that I posed? So you want a T whose second iterate is not ergodic, even though T is ergodic.
Yeah. No, I don't know.
Or can you show me the part of the board that has the equivalent formulations of ergodicity again?
Oh, yeah, that's supposed to be helpful for this. It's too bad I took that away. Well, so I can tell you the main one, which is that the spectral measure gives 0 mass to lambda equals 1.
Does the shift map work? Because if you like take something and like slide a 0 in every other slot, and then you shift it twice, you could have things that don't move around everywhere.
That's a very nice idea. That's not, doesn't quite fit in our domain of discourse because the integers have infinite measure. But that's a very good idea. The action of t on the integers is transitive, but the action of t squared is not transitive. It falls into two orbits. So that's, now we just have to sort of soup that up.
Mm-hmm.
But the phenomena is not deeper than that. Carl, do you have an idea?
I haven't yet, sorry.
Benji, were you suggesting shifting on the integers or taking a shift on some shift space and then squaring it?
Oh, so what I understood Benji to be saying, and maybe I didn't understand right, was if you take t acting on the integers, then this is ergodic in the sense that there's no t invariant set. But if you take shift by 2, this is not ergodic, because you can partition it to the integers. Was that roughly what you were thinking, Benji?
Yeah, I was thinking like the shift on the product of infinite things, because if you can partition that into the things that are like only supported on the evens versus the odds.
I see. So let me see if I understand right. So we take the shift map on like infinitely many copies of the interval from 0 to 1, or maybe the shift map on Z2 to the Z. That's our measure space.
Yes.
Okay, so that's all of these sequences. Right, and then
Then you have these, if you square the shift map, then it has this invariant, this two different invariant subspaces of sequences that are like non-zero only in the even spots or something.
right, but I think that set will have measure 0 in this space.
Yeah.
Can I take us, this is probably related in spirit. Can you take 2 copies of S1 and first irrationally rotate and then jump to the corresponding point of the other copy?
Very nice. Yeah, you can just take the irrational rotation of 2 circles that are disjoint. That's not ergodic. But now if you just rotate one and then swap, that is ergodic. But its square is it preserves the partition of the 2 circles. So.
Oh, we have people coming back.
Oh, yeah. I closed it's almost the end of class, so I closed the breakout rooms. Okay, so welcome back. Anybody want to report on their thoughts on this question? Maybe raise your hand if you are a reporter for your group. Did anyone come back from the breakout rooms yet? There we go. Okay. Great. Okay, so raise your hand if you're a reporter. Okay, so Ben, do you want to report, weigh in?
Yeah, I guess our group didn't really get that far. I mean, mostly just you want to find something with like -1 in the spectrum, but we couldn't really think of an example. But
okay, great. But you got the idea of B, right?
yeah, like roots of unity, I guess. Or, yeah.
Yeah. Okay, so for B, what's the answer?
Just
Yeah, go ahead.
Yeah, I guess if there's like a root of unity in the spectrum. Yeah.
Right, if you have an nth root of unity in the spectrum, a delta mass at an nth root of unity, then it becomes an eigenfunction, an invariant function for the nth iterate. Yeah, so that's exactly what you have to avoid is delta masses at the nth roots of unity. Great, how about Matthew?
Yeah, so one explicit construction that we had is if you take, say, the two-pointed space with the obvious measure, and then you take your transformation to just switch the 2 points. This is ergodic.
Okay, very good. So your transformation is the permutation of 2 points, and its square is the identity. Actually, that's a pretty nice example. Let me ask Yan-Cheng Yang, do you have another example or a more a less finite-istic example?
That's exactly our example. I mean, I guess can generalize it to n.
Okay.
Yeah, that's it.
Does anyone know how to make this into an example with an infinite set or with a measure with no atoms? It's a very good idea that the permutation matrix has eigenvalues which are roots of unity.
So maybe take your favorite ergodic transformation and replace each point by that. And now just compose that transformation with the permutation on 2 components.
Great. Okay. So Carl has nicely weighed in for us. Replace these points by by 2 copies of the same space. For example, the circle where you have the irrational rotation, and then your map could be the identity from one copy to the other, and then your transformation coming back. And now, this map is ergodic because any set that's invariant has to intersect the first factor in an invariant set, so it has to be a full measure, but then the identity map takes it on the other set. But when you square it, you get 2 invariant sets, each of the same measure, just like you had 2 points here. And so in that way, that's basically taking a slightly twisted product of the trivial example. Okay, so next time we will discuss mixing, which is much more robust. It does pass to iterates of T. And you might want to take a look on the web page of the picture called Poincare recurrence, which I will explain next time. Okay, so thanks for coming, and I'll leave the Zoom room open as usual.
I might have missed it. Did anybody mention a connected example for?
Oh, well,
Yeah.
okay, so
I was thinking you could do something with like a 2 torus, but haven't laid it out yet.
I mean, so far this has been a discussion that's purely measure theoretic, so it didn't have to do with connectedness, but yeah. So I think you can make examples that are not totally unnatural, which are connected, having to do with flows on surfaces, but they're I don't know a natural one off the top of my head.
This kind of answers my question, which is along similar lines, but we know what we kind of want the spectrum to look like to some degree. We know we want a point mass at -1, not a point mass at 1. So is there no recipe to go from that to go back to the map that's kind of reasonable to follow?
Yeah, that's interesting. So one thing I haven't emphasized, but which is actually a quite deep problem, is can you start with a spectrum or a unitary operator, then create a measure-preserving dynamical system with that spectrum? And the answer turns out to be no. That for example, if the space is not finite, then the spectrum, if the map is not periodic or has no periodic points, then the spectrum is dense in the circle. So you're tempted to say, I'll just take that thing with Lebesgue spectrum and throw in a point at -1. But nobody knows how to characterize which spectral measures arise from dynamical systems. And I should have said that earlier. So a long-standing problem is to show that, is to find an example that has Lebesgue spectrum of finite multiplicity. So for the torus and all the other examples people have ever been able to come up with, when you have Lebesgue spectrum, it comes with infinite multiplicity.
Cool. Thank you.
Okay, well, good to see you.
Thanks.
I'll have office hours tomorrow and see you on Thursday, if not then.